All right, Honors Chem, we are going to do colligative properties today. And it has a really weird name, and I still haven't figured out the origin for colligative. Sorry, I usually try and figure out the name origin, but I haven't been able to figure out the etymology of this word. Okay, so colligative properties are physical properties of solutions that are affected by the number of particles, but not by the identity or the type of particles. These are called colligative properties. So let me highlight that again. So they're properties, and they're all physical properties that are affected by the number of particles, but not the identity or the type of particles. So it doesn't matter what's dissolved, it just matters how much is dissolved, the number of particles. And they are called colligative properties. Okay? There are 4 colligative properties that we're going to talk about. We're going to talk about vapor pressure lowering. We're going to talk about melting point depression. We are going to talk about boiling point elevation, and we are going to talk about osmotic pressure in that order. Okay? So here we go. Vapor pressure lowering. So experiments show that adding a non-volatile solute, non-volatile means that it has little tendency to become a gas, to a solvent lowers that solvent's vapor pressure. The particles that produce vapor pressure escape the liquid phase at the surface. Remember, we had 2 things that things had to have in order to evaporate. They had to be right at the molecule had to be right at the surface, and that molecule also had to have enough kinetic energy to escape the attraction of its neighboring molecules. Now, think about this. When a solvent is pure, I'm right here, when a solvent is pure, the particles of that solvent occupy the entire surface area, right? When the solute and the solvent are mixed, we have a mix of solute and solvent then on the surface. Okay, so not all the surface area is solvent. Some of it's taken up with the solute. So that means that we have fewer solvent particles at the surface. So fewer particles at the surface mean fewer of those, then, statistically speaking, are going to have enough kinetic energy to escape into the gaseous phase. So the overall effect is that we have a lower vapor pressure. Okay? Thus, the vapor pressure lowering is proportional to the mole fraction of solvent particles in a solution, and it is a colligative property. So normally when we do a mole fraction, we do mole fraction with solute over total moles, but vapor pressuring, we're looking at solvent over total moles. So it's a little bit different than normal. Okay, so here we go. Here is our mathematical formula. So the vapor pressure that we would expect is P2. So this is the vapor pressure of the solution. And boy, I just don't want to write very well today. So let's try that again. Okay, vapor pressure of solution. Okay, P1 is the vapor pressure of the pure solvent. And then MF1 is the mole fraction of the solvent. Okay, so this is our formula. So the pressure that we would expect is equal to the vapor pressure of the pure solvent times the mole fraction of the solvent. So it's just really a proportionality of the mole fraction. Okay, so here's a diagram just to give you an example. So here I have a pure solvent. Notice the whole entire surface area here is just solvent. So we've got a lot of molecules that are able to become part of the vapor phase because we've got all of them on the surface. But notice here, I've got some molecules that are solute, that are blocking the solvent from going into the vapor phase. So I have fewer molecules that are coming up into the vapor phase, so my vapor pressure is lower. Okay, so let's do some calculations here. You are definitely going to want a calculator. So I'm going to grab my handy dandy Totoro calculator. All right, so example 18. If I have 0.1 mole of glucose and I dissolve it in 2 moles of water at 25 degrees Celsius, what is the resulting vapor pressure of the solution? The vapor pressure of normal, like pure water at 25 is 24 millimeters of mercury. So if we look at this fraction, this what is the right word? Formula. Formula is the word I'm looking for. So if I look at this formula, I need to find, first of all, what my mole fraction is. My pressure of my pure solvent is already given to me. So let's work on finding my mole fraction. So my mole fraction, remember, is of the, that's right, it's of the solvent. Okay, so I'm going to, what is my solvent? It's not the glucose, it is the water. Okay, so I've got 2 moles of water. And then mole fraction, remember, is moles of what you're interested in, the number of that, divided by total number of moles. So in that solution, I've got water and the glucose. So I have to put the 2 moles of water plus the 0.1 mole of glucose. Okay, so that's really going to be 2 divided by 2.1, correct? So let's do that mathematically. Okay, 2 divided by 2.1, we get a mole fraction. Let's see, we've got 2 sig figs, so we get a mole fraction of 0.95. That is my mole fraction. Okay, now with that mole fraction, I can plug it in here. Okay, so my original pressure that I would expect of pure water is 24.0 millimeters of mercury. And then I need to multiply it by my mole fraction, which we just calculated, which was 0.95. Okay, so we're going to take 0.95 and we are going to multiply it by 24. I'm just going to use the answer that my calculator had. It gives me 22.8. Now, notice I've got 3 sig figs here, but here I only have 2. So that 8 really is going to tell us to round up. So we're going to report this as 23, and our unit here is millimeters of mercury. Okay, so the pressure that we would expect off of this solution is 23 millimeters of mercury, and we normally get about 24 millimeters of mercury. It doesn't change that much, but it changes a little. Okay, so let's look at number 19. We're going to substitute 0.1 mole of sucrose instead of glucose. So this is table sugar. So our formula is still the same. Our pressure that we would expect would be the original vapor pressure of pure water multiplied by the mole fraction that we would calculate. Now we're still going to do a mole fraction of the solvent, which is water. So we're going to have still 2 moles of water. So 2 moles of water, and then total moles, we have the 2 moles of water. And now I have 0.1 moles of sucrose, C12H22O11. That math sure looks the same, doesn't it? So 2 divided by 2.1, same thing. We get the same mole fraction. We get a mole fraction of 0.95. So our calculations are going to be pretty much the same, aren't they? I start with my 24 millimeters of mercury. I multiply it by my mole fraction of 0.95. And I still am going to, with sig figs, I'm going to get 23 millimeters of mercury. So notice, just like I said up top here, where it doesn't matter. It's not the identity of the dissolved particles, but it is the number of particles. It didn't matter if I was dissolving glucose or sucrose. It just mattered the number. And since the mole fraction for both of those problems, the number was the same, the effect is going to be the same, even though sucrose weighs almost double what glucose does. Okay? It doesn't matter. Okay, now let's look at number 20. Now you're going to think, okay, well we're going to substitute 0.1 moles for sodium chloride instead of sucrose, instead of glucose. Now, this one's kind of tricky. Think about what happens when sodium chloride goes into water. Do you see the thing? So when sodium chloride goes into water, let's get another color here. When sodium chloride goes into water, does it stay as sodium chloride? Think about your net ionic equations. That's soluble, isn't it? All group 1 salts are soluble. So we actually get sodium plus ions, and we get the chloride negative ions. So we actually get 2 particles for the price of 1. Okay, so wouldn't we also have 0.1 moles of sodium, and we would have 0.1 moles of chloride? Do you guys agree with that? So in reality, our mole fraction is going to change. So when we use this, let's look at our mole fraction. So we're still going to use water on the top because that is the solvent. So we have 2 moles of water, but our total changes. So I have 2 moles of water, and I have 0.1 mole of sodium ions, and I have 0.1 mole of chloride ions. So I'm really going to be taking 2 divided by 2.2, right? So when I do that, 2 divided by 2.2, let's see. I will get 90.9, right? 9.909. So my mole fraction will be 0.909. And I know I have just 2 sig figs, so we should really report it like this, right? So when we put this in then, I'm going to take my 24 millimeters of mercury, And I'm going to multiply it by my mole fraction of 0.91. I get a vapor pressure of 21.84, and I only had 2 sig figs, so that 8 is going to tell me to round up. So I'm going to do 22 millimeters of mercury is the pressure that I would expect from that solution. Now notice ionic compounds, we need to think about how they break apart in water. And if I get multiple ions, that gives me a multiplier effect of this mole fraction. Okay, so let's substitute calcium nitrate. Now, is calcium nitrate soluble? Do you remember your solubility rules? All nitrates are soluble, no exceptions. So when calcium goes into water, we're going to get a calcium ion and we're going to get 2 nitrate ions. So we're going to get 0.10 moles of calcium, but we're going to get 0.2 moles of nitrate ions. Do you guys agree with that? So that changes our calculation of our mole fraction a little bit, doesn't it? So let's calculate our mole fraction. So we still have our 2 moles of water. And this time we're going to have our 2 moles of water plus our 0.1 mole of calcium and our 0.2 moles of nitrate. Okay, so I'm going to have 2 divided by 2.3. So that gives me, with, let's see, 2 sig figs, that gives me a mole fraction of 0.87 for my mole fraction. Do you guys agree with that? Okay, so when I do that, I get my 24 millimeters of mercury that I would expect with pure water, multiplied by 0.87 for my mole fraction. That gives me 20.88. Once again, just 2 sig figs, so that 8 tells me to round up. So I would report this as 21 millimeters of mercury for my pressure. Notice the more particles, it doesn't matter what type of particles, but just the more particles, the lower that pressure becomes, because the more that surface area is taken up with the solute particles and the solvent can't evaporate. Okay, so next thing we're going to learn about boiling point elevation and freezing point depression. So the boiling point actually raises up and the freezing point actually goes down when we put solute in there. Okay, so because non-volatile, remember non-volatile means that it doesn't go into the gas phase very easily. Because a non-volatile solute lowers the solvent's vapor pressure, it also affects the boiling point. Remember, to have something boil, the vapor pressure of that solution or that substance has to be equal to the atmospheric pressure. And if we lower the vapor pressure because there's solute particles in the way, that's going to take it a lot longer to actually boil. We're going to have to create a hotter temperature to get more particles to vaporize. So it actually raises the boiling point when we put solute in there. Okay, so recall that a liquid in a pot on a stove boils with the vapor pressure equals the atmospheric pressure. And my computer wants to freeze now. So hopefully it won't take too much longer. Okay, so when the temperature of a solution containing a non-volatile solute is raised to the boiling point of the pure solvent, the resulting vapor pressure will still be lower than the atmospheric pressure. So let's see. We want to put equal in that first line, if it will let me write. Okay, so we're going to start right here again. When the temperature of a solution containing a non-volatile solute is raised to the boiling point of the pure solvent, the resulting vapor pressure will still be below the atmospheric pressure because that solute is getting in the way of those solvent particles vaporizing. Okay? And so the pressure doesn't equal the atmospheric pressure, so it's not going to boil. The solution must be heated to a higher temperature to supply the additional kinetic energy needed to raise the vapor pressure to the atmospheric pressure. The temperature difference between the solution's boiling point and a pure solvent's boiling point is called boiling point elevation. Okay, so here is the formula for the boiling point elevation. We have the change in temperature. Notice it doesn't give us the actual new temperature. It just gives us the change of temperature. So we have to add this change on to the normal boiling point. Okay, so the change in temperature is equal to the boiling point constant for that solvent. Notice we have different solvents and they have different constants. Okay, times the molality. Remember, little m is molality. So we have to calculate molality and we have to multiply by the specific content or constant of our solvent to get just the change. And then we have to add that change to the normal boiling point of that solvent. Okay, kind of complicated. So a solvent's freezing point temperature, the particles no longer will have sufficient kinetic energy to overcome the interparticle attractive forces. So they go into that crystalline structure and become that nice crystalline structure that the particles just vibrate about a fixed point. Those particles form into a more organized structure in the solid state. In solution, the solute particles interfere with those attractive forces and don't let them actually go into that crystalline structure. It kind of messes up the crystalline structure. Okay? This prevents the solvent from entering into that crystalline structure to form that solid state at its normal freezing point. It just kind of messes up that crystalline structure. It's kind of like an impurity that messes up that structure. Okay? So our freezing point depression constants are, once again, very, very specific to that solvent, and the formula is fairly much the same as well. Okay, so when we look at that, our formula is the change of the temperature multiplied by that freezing point constant multiplied by the molality. Okay, so wow. So when we do that, we have to also now we're going to be taking that freezing point constant change and we're going to be subtracting it because it's a depression from the normal freezing point. Okay? So let's see if I can get this off. I don't want to do that. Let's see here. All right, so we're going to leave it. Actually, let's talk a little bit about how this changes the phase diagram. So notice if we raise the boiling point because of this, our phase diagram, we are going to have a much greater area in that liquid state because we will change that pressure and we will be able to create much more area on the liquid state that goes both into the solid area and into the gas area. So our liquid state, when we have solute dissolved into the solvent, becomes much greater. So we lower the freezing point and we raise the boiling point. And we use colligative properties like this. We see this when we have snowstorms here in Salt Lake, and we put salt on the road because that salt will actually break up that crystalline structure and get in the way of that ice and snow to freeze and create ice. And so it keeps the snow liquid even at freezing temperatures because it gets in that way of creating that crystalline structure. And we use that also when we create ice cream. We put salt on that ice, and it actually makes the ice colder so that we actually can freeze the cream and the sugar and the stuff that we have to make ice cream. Okay, my next video, we are going to start practicing learning how to actually do some of these. So see you later.